Welcome. Today we are going to start our third chapter, Calculus on Vector Fields. In our second chapter, we elaborately discussed calculus on scalar fields. Like other studies of calculus, we shall start with the notion of limit, then continuity, followed by differentiability and so on. The first module concerns with limit and continuity of vector fields. First of all, let us recall what do we mean by a vector field. Let us consider a function f defined over a set A where A is a subset of Rn. If the codomain is a subset of R, we call f a scalar field, and if the codomain is a subset of Rn where n greater than 1, we call f a vector field. So, a natural example for a vector field on R3 is the following. At any point in space, we can realize that wind velocity at that point defines a vector field. In spite of considering velocity of the wind, if we consider temperature, we would have a scalar field. Now, we are going to describe what do we mean by components of a vector field. Let A be a non-empty set in Rn and F is a map from A to Rm. Then corresponding to each x, a n-tuple which is a member of A, say x equal to x1, x2 up to xn, there is a unique y equal to fx in Rm. As y is a member in Rm, we can express it as a m-tuple y1, y2 up to ym. If we look at these real numbers y1, y2, ym, they depend on both the choice of x as well as the choice of f. So, these yi's define real valued functions defined on the set A. As all these functions are derived from f and are associated with a particular component I, we prefer the notations yi equal to fix, where x is in A and I runs from 1 to up to m. These functions fi from A to R are called component functions of f. Sometimes we denote this by writing f equal to ordered m-tuple f1, f2 up to fm. Now, we define the notion of limit of vector fields. Let us recall from one variable calculus that if A is a subset of R and C is a limit point of the set A, then a function f from A to R is said to have a limit L, which is a real number, at that point C, if provided any arbitrary positive number epsilon, we can find a delta depending on epsilon and positive such that whenever mod x minus c is positive but less than delta, we must have the difference between fx and L less than epsilon. In other words, if x lies in the open sphere with center C and radius delta, but not the point C, that means if x lies in the open interval C minus delta to C plus delta, leaving the point C, then fx must lie in the open interval L minus epsilon to L plus epsilon. In such case, we write limit of fx as x approaches C is L, or fx tends to L as x tends to C. This notion of limit of a function of one variable can easily be extended in the case of scalar fields as follows. Here, we consider A as a subset of Rn. In the earlier case, we considered A as a subset of R. Let f be a map from A to R. So, f is a scalar field. Let C be a limit point of the set A. A real number L is said to be a limit of the function f at the point C. If given any positive epsilon, we can find a delta depending on epsilon and positive such that whenever norm of the vector x minus c less than delta but positive, we have modulus of fx minus L less than epsilon. That is, whenever x lies in the open sphere with center C and radius delta and it is punctured at its center, then we must have fx in the open interval L minus epsilon to L plus epsilon. In such case, we write limit of fx as x tends to c equal to L or fx tends to L as x tends to c. If we want to use the concept of calculus of one variable, we can rewrite this as limit extending to c fx equal to L if and only if limit as norm of x minus c approaches 0 from the right fx equal to L. So, now we are in a position to generalize the notion of limit of a function in the case of vector field, and it follows. Let A be a subset of Rn, F is a map from A to Rm, that is F is a vector field defined on the set A, and C be a limit point of the set A. Now, a vector field L in Rm is said to be a limit of the function f at the point C if and only if given any epsilon positive there exists a delta depending on epsilon and positive such that whenever norm of the vector x minus c is positive but less than delta, we have norm of the vector fx minus L less than epsilon. That is, whenever x lies in the open sphere with center C and radius delta and punctured at the center, then fx must lie in the open sphere with center L and radius epsilon. Here SNC delta indicates the sphere is in Rn and Sm indicates that the sphere is in Rm. In such case, we write limit extending to C fx equal to L or fx tends to L as x tends to C. Thus, we can say limit extending to C fx equal to L if and only if limit of norm fx minus L equal to 0 whenever norm of x minus c approaches 0 from the right. We have some remarks here. The first one we have already mentioned. In order to distinguish between open spheres in Rn and Rm, we used separate symbols like Sn C delta and Sm L epsilon. Second one, in the above definition, the value of delta usually depends on epsilon. This is why we write delta equal to delta epsilon to emphasize this dependence. Third remark, the inequality 0 less than norm of x minus c less than delta implies that x is different from c. That is, in order to the limit of fx as x tends to c to exist finitely, it may so happen f is not even properly defined at the point C. Next, if L is a limit of f at C, then we say that f converges to L at C. If the limit of f at C does not exist finitely, we say that f diverges at the point C. Now, we claim that the value of the limit, that is the vector L of the vector field f, is unique. So, we have the following proposition. Let A be a subset of Rn, F a map from A to Rm, that is a vector field defined on the set A, and C be a limit point of the set A. We further assume that limit of fx as x approaches C equal to the vector L1 as well as the vector L2, where both L1 and L2 are vectors in Rm. In such case, we must have L1 equal to L2. That is, the limit must be unique whenever it exists. We start the proof. Let us assume, if possible, that L1 and L2 are different. That is, norm of L1 minus L2 must be positive. So, we fix our epsilon to be half the distance between L1 and L2, that is epsilon equal to half norm of L1 minus L2. As L1 and L2 are different, clearly epsilon is positive. As limit of f(x) as x approaches c is L1 as well as L2, then corresponding to this epsilon, we can find delta 1 and delta 2 both dependent on epsilon, such that whenever norm of x minus c less than delta 1 but positive, we have norm of f(x) minus L1 less than epsilon. Similarly, whenever norm of x minus c less than delta 2 but positive, we have norm of f(x) minus L2 less than epsilon. So, we select delta equal to minimum of delta 1 and delta 2. First of all, delta is the minimum of two positive quantities. So, delta must be positive. Delta 1, delta 2 both are dependent on epsilon and delta is their minimum. So, delta is also dependent on epsilon. Moreover, the most important part is, if we consider those x which satisfies norm of x minus c less than delta but positive, then both the above inequalities are satisfied for such x. That is, we consider those x such that 0 less than norm of x minus c less than delta. Then we have norm of L1 minus L2 equal to norm of f(x) minus L2 minus f(x) plus L1. We apply triangle inequality. So, this lesser equal to norm of f(x) minus L2 plus norm of f(x) minus L1. Both of them are less than epsilon. So, summed they are less than 2 epsilon, which is nothing but norm of L1 minus L2. So, we have norm of L1 minus L2 less than norm of L1 minus L2, which leads towards a contradiction. Hence, we must have L1 equal to L2, that is, limit of a vector field, if exist, should always be unique. One observation: let F be a vector field defined in some deleted neighborhood of a point C in Rn, and we further assume limit of f(x) as x tends to C exists and equals to L. Then corresponding to each epsilon positive, there exists delta positive, such that whenever norm of x minus c less than delta but positive, we have norm of f(x) minus L less than epsilon. That is, f(x) belongs to the open sphere in Rm with center radius epsilon. This shows that whenever limit extending to C f(x) exists finitely, f is bounded in some deleted neighborhood of the point C. Now, we are going to observe how the limit of a vector field is related to the limits of its component functions. We recall that the components of a vector fields are nothing but scalar fields defined on the same domain. We have the following theorem. Let A be a subset of Rn. F is a vector field defined on A. The codomain of F is Rm. So, we assume the components of F are F1, F2 up to Fm. We also assume that C equal to C1, C2 up to Cn is a limit point of the set A, and L equal to L1, L2, Lm is a member of Rm. Then limit of f(x) equal to L as x approaches C, if and only if limit of f(ix) equal to Li as x approaches C for every I equal to 1 to m. We start the proof. We first assume that limit of extending to C f(x) equal to L. We shall prove that for every I equal to 1 to m, limit of the scalar fields f(ix) as x approaches C must be Li. Let epsilon greater than 0 be arbitrarily chosen. Then there exists delta dependent on epsilon and positive such that whenever norm of x minus c less than delta but positive, we have norm of fx minus L less than epsilon. In the next line, we write the components of f as well as L, that is, we have norm of f1x up to fmx minus L1 up to Lm, norm of this vector less than epsilon. That is, norm of the vector with components f1x minus L1 up to fmx minus Lm less than epsilon. We write down the value of the norm, that is non-negative square root of summation I from 1 to m mod fix minus li square less than epsilon. Squaring both the sides, we have summation I equal to 1 to m modulus of fix minus li square less than epsilon square. This shows mod of fix minus li square less or equal to sum of these m terms and less than epsilon square. Therefore, modulus of fix minus li square less than epsilon square for each I, that is mod of fix minus li less than epsilon for each I. This implies that for each I from 1 to m, limit of fix as x tends to c equal to li. Now we are going to the other part. Conversely, we assume that limit of fix as x tends to c equal to li, and this holds for every possible value of I. We shall prove that limit extending to c fx equal to L. Let epsilon positive be arbitrarily chosen. Then for each I equal to 1 to m, we can find m many delta i's dependent on epsilon and positive such that whenever norm of x minus c less than delta I but positive, we have modulus of fix minus li less than epsilon. Let delta be the minimum of delta 1, delta 2, delta m. Clearly, delta is positive and also dependent on epsilon. Then for every I from 1 to m, we have norm of x minus c less than delta but positive implies modulus of fix minus li less than epsilon. Now, norm of fx minus L equal to the non-negative square root of summation I equal to 1 to m modulus of fix minus li square, and this is less than square root of m epsilon square, that is square root of m epsilon. Now, epsilon is arbitrarily assigned positive quantity and square root of m is a fixed quantity. So, this shows whenever norm of x minus c is less than delta but positive, norm of fx minus L less than root m epsilon. Now, root m epsilon can be made arbitrarily small. So, this implies that limit of fx as x tends to c equal to L. One remark here, let A be a subset of Rn, F is a map from A to Rm, where F have components f1, f2, fm. So, f1, f2, fm are scalar fields defined on the same set A. C equal to C1 to Cn is the limit point of the set A, and the limit of f at the point C exists. Then in view of the above theorem, we can write limit of fx as x tending to C equal to the ordered M tuple limit extending to C f1x up to limit extending to C fmx. Here, the concept of limit of a vector field is expressed in terms of limits of its components, that is scalar fields. Now, we are going to discuss some easy examples. First one, let f from Rn to Rn be the identity vector field, that is for every x in Rm, fx equal to x. Then we can write fx equal to f1x up to fnx for every x in Rn, So, Fi is the ith component of the vector field F. Sometimes we call this ith projection function of F. So, here we find Fix equal to Fi x1, x2 up to xn, that is xi. Now, for each I equal to 1 to n, we find that limit of Fix as x approaches 0 equal to limit of xi as x approaches the origin, that is 0. Hence, limit of Fx as x approaches the origin equals the n tuple limit f1x up to limit fnx, and in every limit x approaches origin. So, we have 0, 0, 0, 0, that is the origin. Second example, let f from R3 to R2 defined by f of xyz equal to x square y plus z and yz by 1 plus x square for every xyz in R3. Then we can write fxyz equal to the ordertive pair f1 xyz, f2 xyz. Here f1 and f2 both are scalar fields defined on R3. They are the component functions of the vector field f and are given by f1 xyz equal to x square y plus z and f2 xyz equal to yz by 1 plus x square. Now, we consider the limit whenever we are approaching the origin, that is xyz tends to 0, 0, 0. So, we have limit of f1 xyz equal to 0, limit of f2 xyz equal to 0. Therefore, limit of f as the point approaches origin is 0, 0. In the following example, we shall see that it may also happen the limit does not exist. Let f be a vector field defined on the set R2 deleted the origin, and codomain is also R2, and it is defined by fxy equal to ordered pair x square y cube xy by x square plus y square. Then we can write fxy equal to ordered pair f1 xy f2 xy, where f1 xy equal to x square y cube and f2 xy equal to xy by x square plus y square. Evidently, the limit of the scalar field f1 as xy approaches 0, 0 exists, and we have limit xy tending to 0, 0 f1 xy equal to 0, but the limit of the scalar field f2 does not exist as xy approaches the origin. Hence, the limit fxy as xy approaches origin does not exist. Now, we are going to discuss about limits of the vector sums, scalar multiplications, inner products and norms of vector fields. The theorem reads as follows: let A be a subset of Rn, Fg are vector fields defined on the set A and their codomain is Rm, and C is the limit point of the set A. We assume the limits of f and g both exist as x approaches C. Let limit of fx equal to L1 and limit of gx equal to L2 as x tends to C. Then, the limit of the vector field f plus g exists at the point C, and we find that limit extending to C f plus gx, that is fx plus gx equal to L1 plus L2, which is nothing but limit of fx plus limit of gx as x tends to C. That is, if the limits exist, then limit of sum equals sum of limit. Similar result holds for difference. Now, if A is a real number, then limit of the vector field AF as x approaches C also exists, and its value is A times L1, that is A limit of fx as x approaches C. Also, the limit of the inner product fx and gx x approaches C exists and its value is inner product L1 L2, that is inner product of limit of fx and limit of gx as x approaches C. So, whenever the limits exist, limit of inner product equal to inner product of limits. Similar result holds for norm also. So, limit of norm fx as x approaches C equal to norm of L1 equal to norm of limit of fx as x approaches C. So, up to this part of this module, we have discussed limits of vector fields. Now, we are going to discuss continuity of vector fields. Now, we are going to discuss continuity of vector fields. We recall from calculus of real valued functions of one real variable that for a subset of R and C is an interior point of the set A function f from A to R is said to be continuous at that point C if and only if limit of fx as x tends to C exists finitely and equals fc. That is, corresponding to every positive epsilon, we can find a delta such that whenever mod x minus c less than delta, we have mod fx minus fc less than epsilon. That is, whenever x is in c minus delta to c plus delta, we have fx in the open interval fc minus epsilon to fc plus epsilon. Now, we say that a function f from A to R is continuous if and only if f is continuous at every point of that set A. This notion of continuity of a function at an interior point of its domain can be easily extended in the case of scalar fields. We discussed it earlier, here we recall. Let C be an interior point of a set A where A is a subset of Rn and f is a scalar field defined on the set A. Then f is said to be continuous at the point C if and only if for every epsilon positive we can find a delta such that if norm of x minus c is less than delta, we have mod of fx minus fc less than epsilon. That is, whenever x lies in the open sphere with center C and radius delta, fx lies in the open interval fc minus epsilon to fc plus epsilon. That is, if and only if the limit fx as x tends to C exists finitely and equals fc. If a scalar field f is continuous at every point of a set A, we say that f is continuous on the set A. Now, we generalize the notion of continuity in the case of vector field as follows. Let A be a subset of Rn, f is a map from A to Rm and C is an interior point of the set A. Then the vector field f is said to be continuous at C if and only if for every epsilon positive there exists a delta dependent on epsilon and positive such that norm of x minus c less than delta implies norm of fx minus fc less than epsilon. That is, if the limit fx as x tends to C exists and equals fc. Equivalently, we can say if and only if limit of norm of fx minus fc equals 0 as norm of x minus c tends to 0 from the right. If a scalar field f is continuous at every point of a set A, then we say that f is continuous on the set A. One remark: a function which is not continuous at a point of its domain of definition is said to be discontinuous at that point. Next remark: we suppose that f is a vector field and C is an isolated point in the domain of the function f, then f is considered to be continuous at that point C. Now, we show how the continuity of a vector field is related to the continuity of its components. We again recall that components of a vector field are scalar fields defined on the same domain. Theorem: the statement reads as follows: let A be a subset of Rn, f is a vector field on A, where the components of f are f1 up to fm, c equal to c1 up to cn is an interior point of the set A, then we say that f is continuous at C if and only if each of its components f1 up to fm are continuous at that point C. We give the proof. We first assume that the vector field f is continuous at this point C. Then we have limit extending to Cfx equal to Fc. Now, for each I running from 1 to m, let Ei denote the ith unit coordinate vector in Rm. Then for each I, the component function Fi can be expressed as Fix equal to inner product Fx and Ei for each x in Rn. Then for each I from 1 to m, we have limit extending to C Fix equal to limit inner product Fx Ei. So, this is nothing but inner product of limit of extending to C Fx. If I take the limit of Ei, it remains as it is. So, we have the value of the limit equal to Fic. This implies that for every possible value of I, the ith component function Fi is continuous at C. Conversely, we assume that for each I from 1 to m, the ith component function Fi is continuous at C. Now, we know we can write Fx equal to summation Fix Ei, where I runs from 1 to m. Therefore, limit of Fx as x approaches C equal to limit of sum I from 1 to m Fix Ei. Now, limit of sum equal to sum of limits, we apply it here. So, finally, we get sum Fic Ei, which is nothing but Fc. This implies that the vector field f is continuous at the point C. Now, we cite an example. Let f be the identity vector field on Rn, that is Fx equal to x for every x in Rn. Now, for I from 1 to n, we find that Fix equal to xi. So, if we consider the limit Fix as x tends to 0, its value is 0. Therefore, limit of Fx as x approaches 0, we have it is nothing but the origin, that is f0. Hence, f is continuous at the origin. We can check that f is continuous at any point in Rn. Next example. Let f from R3 to R2 be a vector field defined by Fxyz equal to x square y to the power 5 z plus 1, y square z to the power 7 by 1 plus x to the power 4 for every xyz in R3. Then we can write Fxyz equal to f1 xyz, f2 xyz for every xyz in R3, where f1, f2 are component functions that is scalar fields on R3, where f1 xyz equal to x square y to the power 5 z plus 1 and f2 xyz equal to y square z to the power 7 divided by 1 plus x to the power 4. Now, considering limit as xyz tends to 0, 0, 0, we find that the limit of f1 exists and is 1 and the limit of f2 exists and is 0. Therefore, we find that limit of fxyz as xyz tends to 0, 0, 0 equals with f0, 0, 0. This shows that the vector field f is continuous at the origin. Now, some results regarding continuity. Let A be a subset of Rn, C is an interior point of the set A and Fg are two vector fields defined on the set A, which are also continuous at that point C. That is, limit of Fx as x tends to C equals Fc and similar result for G also. Then we have their sum f plus g, their difference f minus g, both are continuous at the point C. Theorem. Let A be a subset of Rn, C is an interior point of the set A and Fg are two vector fields defined on the set A which are continuous at the point C. That is, limit of f(x) and limit of g(x) as x tends to C exist and equals with f(c) and g(c) respectively. Then, the sum function f plus g as well as the difference function f minus g both are continuous at the point C. For any real number a, the vector field Fs is continuous at C. Finally, the inner product of f and g is also continuous at C and consequently norm f is also continuous. Another result. It reads as follows: a vector field which can be expressed as a restriction of a linear transformation is continuous. We give the proof here. Let U be a subset of Rn and F is a vector field defined on the set U which is a restriction of a linear transformation T defined over Rn. Then we can write F is nothing but restriction of T over U, that is, for all x in U, Tx equal to Fx. Let A be an arbitrary point in the set U and we denote the standard basis of Rn by E1 into En. Then for every x in U we have norm of Fx minus Fa, that is norm of Tx minus Ta. As T is linear, we can write this as T times x minus A. Now we write down x minus A in extended form, that is summation I equal to 1 to n xi minus ai ei. Therefore, the expression becomes equals norm summation I equal to 1 to n xi minus ai tei, and by triangle inequality it is lesser equal to summation I equal to 1 to n modulus xi minus ai times norm tei. So, it is lesser equal to m times summation I equal to 1 to n mod xi minus ai, where m is the maximum of all ti's, where I runs over from 1 to n. Therefore, norm of Fx minus Fa using Cauchy-Schwarz inequality, it is lesser equal to m times root over n norm of x minus A. Now, let epsilon be arbitrarily chosen. Then from the above we can find that whenever norm of x minus A lesser equal to epsilon divided by m root square root n, then norm of Fx minus Fa lesser equal to epsilon. This shows that f is continuous at that point A. Now, the point A was arbitrarily chosen from the set U, thus f is continuous on the set U. Next result. Composition of two continuous vector fields is again continuous. We give the proof. Let C be a point in a set A where A is a subset of Rn and F is a vector field from A to Rm and G is a vector field from B to Rp, such that domain of G contains range of F. Moreover, both are continuous at the point C and Fc respectively. Then the composite vector field G compose F is a vector field from A to Rp where A is a subset of Rn, and we have to prove that it is continuous at C. Now, norm of G compose F x minus G compose F c equals with norm of G of Fx minus G of Fc. Let epsilon be arbitrary. Since G is continuous at Fc, we can find a delta dash corresponding to epsilon such that norm of Fx minus Fc less than delta dash implies G of Fx minus G of Fc norm less than epsilon. Moreover, since f is continuous at C corresponding to delta dash, we can find a delta positive such that norm of x minus c less than delta implies norm of Fx minus Fc less than delta dash. We combine these two. So, corresponding to arbitrary epsilon, we can find a delta such that norm of x minus c less than delta implies norm of G composition Fx minus G composition Fc less than epsilon. Therefore, G composition F is continuous at the point C. So we have discussed continuity of a vector field and its basic properties. With this module comes to an end.